All right, tonight what we're going to be talking about is bond polarity. And what bond polarity is it's the measurement of how electrons are shared between elements. So when two elements have a transfer or somehow are sharing electrons, how are they shared? Are they shared equally? Are they totally given? Or are they totally taken? Or is it an unequal share of these electrons? And how to identify how the sharing occurs is based off of purely the element's electronegativity. And if you remember from the previous semester, electronegativity is the ability of an atom to attract electrons to itself. So what that means is it's how likely or how much does it want those electrons compared to another element. Does it want it more? Does it want it less? So what you want to do is you got to remember that fluorine was the most electronegative and cesium was the least electronegative. Remember that fluorine wanted those electrons most, so if it's ever sharing, it really wants those electrons, whereas cesium really doesn't want electrons, so it gives it up. Now remember that noble gases have 0 electronegativity value, meaning that they never ever want an electron. Okay, why? Because they have a full octet, so they're never ever going to want to gain an electron. Okay. Now the electronegativities decide what type of bond two elements will have, and you have 3 options. You have nonpolar covalent, polar covalent, and ionic bond. If you remember from previous units, covalent bonding is when you're sharing. So we have 2 types of bonds that exist when you're sharing the electrons, nonpolar and polar. And then ionic bonding, if you look at that word ion, which means that you have a positive or a negative charge, what's happening with that is that the electrons are not being shared. Instead, one atom is entirely giving up its electron to another atom. Okay, so ionic bonds are where it is a give or take of electrons. Okay, and then now we need to talk about the sharing. So there's 2 types of ways to share. So you can either share equally, where it's a 50-50 split, or you can share unequally, where it's like a 30-70 split. And what I always try to equate is like driving a car. If you and your sibling have one car and you're trying to share it in between each other, do you do a 50-50 split, or does sometimes the older sibling get the car more often, or the person who has a job get the car more often than the others? If it is a 50-50 split, meaning you get it 50% of the time and your sibling gets it 50% of the time, that would be considered a non-polar covalent bond. If it is more of a 70-30 where it is not equal, that is considered a polar covalent bond. And another term that I try to think of with polar is I try to think of it as a pull. So there is a pull of the electrons going in one direction. So a nonpolar would be there's no pull of the electrons going in one particular direction. It's being split evenly. All right, so here's a visual of if the green area were the electrons, what would it look like? A nonpolar covalent, if you look at it, is perfectly split between the 2 different atoms. So it would be a 50-50 split. That would be polar or nonpolar covalent. So they're both sharing it. That's where the covalent comes from. And it is nonpolar because there's no pull going towards one particular atom versus another. Polar covalent, even though they are sharing, what's happening there is that, if I were to outline it, as you notice, there's a bigger pull going towards that atom on the right. And how do you show that there's a bigger pull is you do this delta with a negative sign. It's a lowercase delta, which is a Greek letter. And that negative means that the charge over on this side is negative. On the right side is more negative. And then delta positive, you always partner it up with a delta negative and a delta positive. The delta positive shows that there's a slightly more positive charge on this side. Why? Because more of its electrons are being donated from this guy on the left to the guy on the right. So this would be a polar covalent. As you can see, there's a pull of electrons going more towards the right one. So I would say and know that that was the more electronegative element. And then we have ionic. Ionic is the 3rd type of bond that you can have, and that is where there's an entire give or take of electrons. So on the left guy, that guy being the positive, obviously gave up its electron to the one on the right. Now, how do you determine whether it's going to be ionic or polar or nonpolar? And that is all based off of the electronegativity difference. So the difference in value, or the subtraction of the two different atoms' electronegativity values. If it is less than or equal to 0.5, we are going to, in this class, call it nonpolar. If it is between 0.5 and 2.1, then it is going to be considered polar. And if it is 2.1 or greater, that is going to be considered ionic. So the greater the electronegativity difference, the more ionic tendencies it will have. All right, so how do you figure this out? I'm going to show you 3 different samples. Okay, F2. So what you're going to do is for F2 is you're going to find F on the periodic table and look at its electronegativity value. So the electronegativity value in this is 4. So I'm going to be comparing my electronegativity of one F, which is 4, to an electronegativity of the other F, which is also 4. And for this one, the difference, which is the subtraction, is 0, which means that it is entirely, completely, 100% a nonpolar bond. So what that means is that all of those electrons are being shared equally between the two Fs. No one F is overpowering the other, which makes sense. All right, now between HF, what you're going to do is find your H, and H is 2.1, and you're going to find your F, and F is 4.0. So to find the difference, you're going to take the larger minus the smaller, and you get a difference of 1.9. So looking back at my ranges, 1.9 falls under here, which is the polar covalent range. So I would write down that this bond would be polar covalent, which means that there is a pull of electrons going towards one of the elements. Okay, so one of the elements is hogging more of the electrons. Even though they're sharing them, it's not entirely equal. Now, which one will it be towards? Well, it'll be towards the bigger electronegativity value, or the one that is more electronegative. And so all you have to do is compare your values. So for F we have 4, for H we have 2.1. So in this case, it is going to be going towards the more electronegative F. And then now we're going to compare Na versus Cl. Na has an electronegativity value of 0.9. Cl has an electronegativity value of 3.0. So I find their difference, which is 2.1. And according to this lovely chart on the other page, we notice that 2.1 or equal or greater is going to be ionic in nature, so that's why this would have an ionic bond, which means that Na entirely gives all of its electrons to Cl. All right, how do you show that there is a pull going towards one individual element? What you want to do is, this is for only polar bonds. For nonpolar, you do not show this. For ionic, you do not show this. This is entirely for only polar bonds. So there's 2 different ways that you can do it. You can either use the delta with the positive and the negative. Once again, the one that's more delta negative is the one that is a higher electronegativity value. So in a chemist's eyes, what it's saying is that F has a higher electronegativity, and it is having an unequal share of electrons, where the electrons are more found on F than on the other one. The other way you can do it is with an arrow, and you point the arrow towards the more electronegative number. And so this one tells you that even though they're sharing those electrons, they're going more towards the F at any particular time than the H. All right, hopefully you understand the bond polarity.